Hello, my name is Sung Hong, and I am a member of XXL Lab. Today I will be presenting a seminar on BAMM Bidirectional Autoregressive Motion Model, which was recently introduced at ECCV 2024. Here's the outline of today's talk. First, I will introduce the concept of text motion generation, followed by some background on the methods that have been explored in this area. Next, I will explain the BAMM model, the core of this research, and how it advances the field. Finally, I'll conclude it. Let's begin by understanding what text-to-motion generation is. Text-to-motion generation is a process where natural language descriptions are converted into 3D human motion sequences. This field is gaining attention because it simplifies the creation of complex animations, making it accessible for applications in gaming, virtual reality, and other domains. For example, instead of manually animating a character or using expensive motion capture systems, you can just describe the motion in the words and let the model generate it for you. To elaborate, text-to-motion generation enables us to create motion directly from text. As the slide shows, if you input a figure walks forward in a zigzag pattern, stepping over something along the way, the system generates a motion sequence that matches this description. This capability has immense potential, particularly in industries where speed and flexibility in creating animations are critical. There are two main approaches that have been used in text-to-motion generation. First, we have BAMM. This method breaks motion into pieces to interface tokenized them and predicts the next tokens, much like how GPT model process language. Second, there's the diffusion model, which generates motion frame by frame, adding and removing noise at each time. Both approaches have made significant contributions to the field, and each comes with each one's strengths and limitations. When comparing these methods, BQVAE has recently shown better performance in text-to-motion tasks. For example, on the human ML3D dataset, which is one of the largest datasets in this field, the top performing models are based on BQVAE. So why does BQVAE better perform? It is truly based on my opinions. One key reason is data efficiency. Diffusion models typically require a large amount of data to achieve high-quality research, which works well in areas like image generation where datasets are abundant. But in text-to-motion, even the largest dataset, human ML3D, has fewer than 15,000 samples. The amount of available data is a critical factor in generative modeling. As illustrated here, diffusion models thrive when there's a wealth of data, but with the limited data available for text-to-motion tasks, BQVAE stands out as the more practical solution. This is one of the reasons why the field has increasingly shifted toward BQVAE. Now let's move into the background of this research. To understand BAMM, we first need to examine the foundation it builds upon. One of the core technologies here is BQVAE. This method is key in converting continuous data into discrete representations, a process known as quantization. By assigning unique identifiers to the segments of data, BQVAE allows us to represent complex motion sequences as numerical tokens, making them easier to process and predict. BQVAE operates using a reconstruction task where it learns to reproduce the original input after converting it into latent tokens. In the case of motion data, the process starts by feeding 3D motion sequences into an encoder. These sequences are then broken down into discrete latent vectors, represented as a series of numbers such as 1, 2, 3, and so on. These numbers are what we refer to as tokens. This approach simplifies complex motion data, making it computationally efficient to work. Tokens are converted back into latent vectors through a process called dequantization, and the decoder uses these vectors to restore the original motion. These tokens can also serve as input for other models, such as transformers, which are designed to predict the next token in sequence. Continuing with ECCV, the tokens generated through quantization play a crucial role in motion generation. Once motion data is tokenized into discrete latent vectors, these tokens can then be used as input for models such as transformers. For example, in this diagram, we start with a text input like "he is flying kick with his left leg." The text is first processed into tokens using models like CLIP. These tokens, along with the motion tokens, are passed into transformer layers, which predict the corresponding motion sequence step by step. While traditional models like ECCV-based models rely on unidirectional generation, predicting one token at a time based on past inputs, this often limits their ability to consider the broader context of the motion. Current SOTA model MoMask introduced a bidirectional generation mechanism. By leveraging masked transformers, it predicts tokens not only from past tokens but also by incorporating future tokens. This innovation reduces error accumulation and significantly improves the quality of generated motions, making it a state-of-the-art approach in text-to-motion generation. Now let's move on to BAMM, the Bidirectional Autoregressive Motion Model. This model was developed to address limitations in existing state-of-the-art methods like MoMask. BAMM focuses on improving the complexity and practicality of motion generation, especially in scenarios where ground truth motion lengths are unavailable or unreliable. Existing models such as MoMask rely heavily on the ground truth length of the motion for generation. For instance, as seen in this example, MoMask generates a motion sequence strictly based on the predefined total number of frames. While this approach works well for research, it can feel unnatural and impractical for real-world applications where such information may not always be available for accurate. This is where BAMM provides a more versatile solution. BAMM introduced a bidirectional autoregressive approach. Unlike unidirectional methods, which predict tokens sequentially in a fixed order, BAMM combines bidirectional attention with autoregression modeling. This allows the model to utilize future context while maintaining the strengths of sequential generation. The diagram shows how bidirectional causal masks differ from traditional unidirectional ones, enabling more comprehensive context use without relying solely on ground truth motion lengths. The next few slides explain the bidirectional causal mask in detail. The generation starts with a unidirectional causal mask, where the model processes tokens in a left to right sequence. This is similar to traditional autoregressive. The black areas indicate what the model can see or attend to at each step. The white areas, on the other hand, represent parts of the sequence that the model cannot see tokens. As shown in the diagram, some tokens in the sequence marked in brown are randomly masked during training. These masked tokens represent parts of the sequence the model needs to predict. The random masking encourages the model to rely on both preceding and succeeding tokens to fill in the gaps, which is critical for understanding the broader context of the motion sequence. In this step, we focus on how the query operates under the bidirectional causal mask. Here, the model ignores masked parts in the query while predicting the next token. The black areas in the diagram represent the parts of the sequence that are visible to query. These are the tokens that the model actively uses for prediction. However, white areas which correspond to masked tokens are entirely excluded from the query's attention. Finally, in the key attention, the model attends to all unmasked tokens, including those in the query. In the diagram, the black areas indicate the unmasked tokens that are fully visible to the key. Unlike the query, the key allows attention to all visible tokens in the sequence, enabling the model to learn relationships between both preceding and succeeding tokens effectively. This design allows the model to leverage a richer context for precision during the bidirectional refinement process. BAMM uses a bidirectional autoregressive approach, which combines traditional unidirectional generation with a bidirectional causal mask. During training, the model randomly masks 50 to 100,000 and 100% of motion tokens, training it to predict missing tokens using both past and future context. In inference, the model first generates motion tokens autoregressively. After that, even indexes tokens are masked, and the bidirectional approach is applied to refine the motion. This two-step process enables the model to handle scenarios where ground truth motion lengths are unavailable while maintaining high quality and coherent motion sequences. The results clearly highlight BAMM's effectiveness compared to BMask. Two key metrics are highlighted here. FID measures the quality of the generated motion by comparing statically simulated between the generated motion and real motion distributions. Lower FID scores indicate higher quality and realism. MMDist evaluates how well the generated motion aligns with the given text prompted. It quantifies the semantic consistency between the text and motion. Lower MMDist values indicate better alignment with the intended text description. BAMM achieves better performance in FID and MMDist. Importantly, this performance is achieved without using ground truth motion length information, which BMask relies on heavily. This demonstrates BAMM's ability to generate better in real-world applications where such information may be unavailable. Now let's look at the impact of iterations in BAMM's inference process. Our precision measures how accurately the generated motions match the input text. Higher our precision values indicate a better match between the motion and the given description. Diversity measures the variety of motions generated by the model for different prompts. Higher diversity scores suggest the model is capable of producing unique and non-repetitive motions. MM modality evaluates the model's ability to generate multiple diverse motions for the same input text, reflecting how well it captures the natural variability in motion. One iteration uses only the unidirectional causal mask without refinement, resulting in reasonable performance. Two iterations, which include one step of bidirectional refinement, show significantly improvements in metrics like R precision and FID, as well as diversity and modality. This iterative refinement process ensures both flexibility and high-quality motion generation. One of the unique strengths of BAMM is its capability for motion editing, which is made possible through its bidirectional generation process. Unlike traditional unidirectional autoregressive models, BAMM enables dynamic editing of motion sequences by leveraging bidirectional attention. Motion editing consists of various techniques, including in-painting, out-painting, prefix, and suffix. In-painting is the text that filling in missing parts of motion sequence as seen in example A, and out-painting is the task that extending motions outward, such as contouring a character's movement beyond the original bounds shown in B. And the prefix task is that adding motion to the start of sequence to create a completion action, as is in C. And the suffix task is finishing the motion sequences at the end, masking in more natural and coherent shown in D. BAMM achieves state-of-the-art research in motion editing tasks, performing models like MoMask and MDM, as demonstrated by its ability to generate smoother and more natural transitions across these operations. To conclude, let's recap the contributions and limitations of BAMM. To summarize, BAMM offers several key contributions. Each achieves outstanding performance even in the absence of ground truth motion length information. Each motion editing capability set a new standard, making it highly adaptable to practical applications. However, one limitation is its relative slow inference speed due to the two-step process involving autoregressive generation and bidirectional refinement. Thank you for your time and attention. Thank you.